In 1966, some of the absolute smartest computer scientists on the planet thought they could teach a machine to see the world over a single summer break.
Which is just wild to think about now.
Right. I mean, they literally set it up as an undergraduate project at the MIT AI lab. The whole plan was to just, you know, attach a camera to a computer, hand it over to the students, and basically say, hey, write a program to make the machine describe what it sees.
Yeah, they genuinely assumed it would be an easy problem to solve, just a quick summer assignment.
Exactly. And now, decades later, we realize that teaching a machine to quote unquote see is actually one of the most complex mathematical puzzles in human history.
It really perfectly captures the sheer hubris of early computer science, doesn't it? I mean, back then we just thought vision was a hardware problem. Like, if we just build a better electronic eye, the computer will automatically understand the physical world.
Right, but the reality is so much more complicated. So, welcome to the deep dive. Today, we are taking a massive stack of research spanning decades of computer science, physics, and biology, and our mission is to unpack exactly how we actually solved this puzzle.
Because it's a huge puzzle.
It is. We want to know how we took machines, which, let's be honest, at their core are just rocks made of silicon, billions of microscopic switches turning light into math, and taught them to not just capture a grid of pixels, but to deeply understand what those pixels actually mean.
And that distinction is crucial.
Okay, let's unpack this. Because it's one thing to teach a computer to capture a static photograph. It is an entirely different universe to teach it that the pixels in that photograph represent, say, a dog catching a frisbee in three-dimensional space.
Right. And what's so fascinating here is that this transition isn't just about cameras at all. It's really about the disentangling of symbolic information from raw data.
Disentangling symbolic information.
Exactly. And to do that, scientists have had to construct these incredibly complex models using geometry, physics, and learning theory. It's this massive interdisciplinary effort. And I actually ask you, the listener, to think about that as we go through this today. What stands out to you when you consider that the devices around you are just constantly, relentlessly trying to interpret your physical world?
It's honestly kind of mind-blowing when you start looking at the real mechanics of it. And to really appreciate the invisible systems running on your phone or in your car right now, you have to look at why that 1966 summer project failed so spectacularly.
Oh, it completely crashed and burned.
Yeah. And I was thinking about this. It's like assuming that because breathing is totally effortless for human beings, building a fully functional artificial lung from scratch is just a fun weekend DIY project for a college kid.
That is a great analogy.
Because seeing is so instinctive for us, we just naturally assumed it would be computationally simple for a machine.
Which I think reveals a really profound truth about artificial intelligence in general. The things that are traditionally hardest for computers,
Yeah.
like calculating the exact trajectory of a rocket to the moon, are very difficult for us humans.
Right, I certainly can't do that math in my head.
Exactly. But the things that are easiest for us, like instantly recognizing a familiar face in a crowded room,
Uh-huh.
or just telling the difference between a flat shadow and a solid object.
The stuff a toddler does without trying.
Right. Those things require millions upon millions of data points for a machine to process.
So the summer of 66 comes and goes. The undergrads, shocker, do not solve human vision.
Yeah.
And the field actually has to slowly grind forward decade by decade.
Very slowly.
Yeah, by the 1970s, they weren't even trying to recognize faces anymore. They were literally just trying to write algorithms that could detect basic edges and straight lines, just looking for the boundaries of objects.
Because without a boundary, an object doesn't actually exist to a computer. It's just a meaningless sea of color.
Wow.
And then, as we move into the 1990s, the focus really shifted to rigorous mathematical optimization. To get a computer to understand 3D space, researchers had to start borrowing concepts from a field called photogrammetry.
Okay, this is a great concept to pause on because photogrammetry sounds incredibly dense.
Yeah.
But it's basically just the science of making 3D measurements from 2D photographs, right?
Precisely. I mean, if you take a picture of a building from the front and then another picture from the side, your human brain naturally understands the 3D shape of that building.
We just stitch it together in our heads.
Right. But a computer doesn't. So they use this concept called bundle adjustment theory.
Bundle adjustment.
Yeah, it's this incredibly heavy mathematical process used to calculate the exact angle and position the camera was in for every single shot. Once the computer calculates exactly where the camera was in space, it can triangulate the light and build a sparse 3D reconstruction of the whole scene.
That sounds like a staggering amount of math just to know what a building looks like.
It is.
But even with all that 3D math, the real modern breakthrough, the thing that brought the field to where it is today, was the shift to deep learning and CNNs, right?
Yeah.
Convolutional neural network.
Absolutely. CNNs changed everything.
And I really want to make sure we explain how a CNN actually looks at an image, because it fundamentally changed the game.
Yeah.
Before this, programmers were manually writing code saying, okay, look for a circle, now look for two eyes.
Which is just impossible to scale. You simply can't write a manual rule for every single object in the universe.
Right.
So a convolutional neural network does something entirely different. Imagine you're sliding a tiny mathematical magnifying glass. They call it a filter over an image, just pixel by pixel.
Scanning the whole thing.
Yeah. And the first layer of the network just uses that filter to look for something super basic, like a horizontal line. Then the next layer takes those lines and looks for a curve.
Building up.
Exactly. The next layer combines lines and curves to find a shape, like, say, a wheel or an ear. It literally builds visual comprehension from the ground up entirely on its own.
And it works. I mean, when you look at massive benchmarks like the ImageNet Challenge, which tests AI on millions of images across 1,000 different object classes, deep learning models now perform basically close to the level of humans.
Close to humans, yes, but they still make some truly bizarre mistakes.
Oh, totally.
Like, these advanced algorithms can easily categorize a highly specific, fine-grained breed of dog or a rare species of bird something most normal humans would completely fail at.
Right, it's superhuman at trivia.
Exactly. But they still struggle immensely with tiny details that you or I would process without a second thought. For instance, a small ant resting on a flower stem.
Oh, interesting.
Yeah, to a CNN, the ant might just look like noise,
Yeah.
or a glitch in the stem's texture. It misses the context entirely.
Or think about images distorted by camera filters. Like if someone puts a weird sepia tone or a heavy glitch effect over a photo on social media, a human looks past the filter instantly. We just know, oh, it's a person with a weird filter.
Right.
But that same filter can completely trip up the neural network because the foundational pixel colors have drastically changed.
And the reason for this limitation goes right back to the fact that pure mathematics just wasn't enough to solve the problem of true visual understanding.
Math only gets you so far.
Exactly. Researchers eventually realized they had to bridge the gap between silicon hardware and biological wetware. To really teach a machine to see, they had to start borrowing heavily from nature.
Which means crossing over into entirely different scientific disciplines. I mean, just to design the physical image sensors that capture the light in your smartphone camera, we have to rely on solid-state physics and quantum mechanics.
It's incredible when you think about the layers involved.
It really is. Physics explains how the light bounces off a coffee cup on your desk, and then quantum mechanics is required to fully understand how those individual photons hit the digital sensor and convert into an electrical charge.
But the biological inspiration is where the real leap in computational processing happens. Neurobiology has massively influenced computer vision over the decades.
Because we had to study ourselves first.
Right. Over the last century, scientists have extensively studied mammalian eyes, neurons, and how the physical brain processes visual stimuli. And that research led to an early direct inspiration in the 1970s called the neocognitron.
Right, developed by Kunihiko Fukushima. This was an artificial neural network specifically designed to mimic the primary visual cortex of the actual brain.
Yes.
And to understand how these biological-inspired networks learn, and frankly, how they fail, there is a brilliant sort of simplified example from the research regarding how a network learns to detect objects. Let's look at the starfish and the sea urchin.
Oh, this is a classic way to explain it.
It makes so much sense.
So imagine you are training a neural network to tell the difference between a starfish and a sea urchin. You feed it hundreds of images of both. Over time, the network creates nodes, these little decision centers, representing visual features.
Okay.
For the starfish, it strongly correlates a ringed texture and a star-shaped outline. For the sea urchin, it matches a striped texture and an oval shape.
Seems totally logical. Starfish equals rings and stars. Sea urchin equals stripes and ovals. It's just assigning mathematical weights to those physical features.
It is. But here is the catch. What if, during that massive training process, there happens to be a single sea urchin image that has a slightly ringed texture instead of stripes?
Just a weird anomaly in the training data.
Exactly. The network creates a weakly weighted association. It essentially notes, okay, a ringed texture might occasionally mean sea urchin.
Okay, I see where this is going.
Right.
Yeah.
Now, you run the train network on a brand new image. It correctly spots a starfish in the sand because of the strong ring and star signals. But because of that one weird training image, the ringed texture of the starfish also sends a tiny, weak signal suggesting there might be a sea urchin nearby.
The machine is getting a little confused.
Yeah. And now imagine a completely random oval clamshell is sitting next to the starfish in the image. The network wasn't trained on clamshells at all.
But the clamshell is an oval.
Yes, and the oval shape of the shell triggers the sea urchin's strong oval node.
So it takes the weak ring signal from the starfish and combines it with the strong oval signal from the clamshell.
Exactly. And suddenly the network outputs a completely false positive. It confidently declares there is a sea urchin in the photo when it's really just looking at pieces of a starfish in a shell.
Here's where it gets really interesting to me, because that mechanism is so fundamentally human.
How so?
It completely reminds me of teaching a toddler to speak. If you only ever show a toddler brown dogs and you point and tell them dog, the very first time they see a brown cat walking down the street, they might confidently point and say dog.
Oh, that's perfect. Yes.
They're overweighting the wrong features, the color brown and the fact that it has 4 legs, and they are completely ignoring the shape of the ears or the tail. It's the exact same false positive as the neural network.
And if we connect this to the bigger picture, what we're really seeing here is an incredible interdisciplinary feedback loop.
It really is.
The study of biological vision helps us build better computer vision algorithms. And in turn, designing these complex artificial neural networks actually gives neuroscientists a working, testable model to understand our own neurobiology. We are essentially reverse engineering ourselves.
So we have the biological inspiration from the brain, and we have the quantum physics in the camera sensors. But how does a modern system practically process an image in the real world, like step by step?
The actual mechanics of it.
Yeah, let's walk through the actual pipeline. But first, I think we really need to clarify the difference between image processing and computer vision, because I hear them conflated all the time.
That is a crucial distinction to make. In image processing, the input is an image, and the output is just an enhanced image.
Like Instagram filters.
Exactly. Think of hitting the auto-enhance button on your phone, adjusting contrast, rotating a photo, or removing background noise. The computer doesn't actually know what is in the picture. It's just blindly manipulating light values. Computer vision, on the other hand, takes an image or video as input, and the output is a decision. It's a 3D model, an analysis, or a specific system behavior based on what it actually understood.
Okay, so the output of computer vision is an action. So how do we get from raw light to a concrete decision?
There is a very strict 5-step pipeline these systems go through.
To make this concrete for you listening, let's use a real-world example as we go through the steps. Let's imagine a camera on a sterile factory line inspecting microscopic wafer computer chips for tiny defects.
Perfect example. So step 1 is image acquisition. Now, this isn't just a standard webcam. Depending on the application, it could be LiDAR, radar, or ultrasonic sensors.
But in our factory example,
In the factory, it's likely a high-resolution microscopic camera capturing the raw photon data reflecting off the silicon wafer as it moves super fast down the conveyor belt.
okay, so it snaps the raw data. Then comes step 2, pre-processing. Before the heavy lifting begins, the system has to clean up that data, right?
Yes. It might remove the glare from the harsh factory lighting or enhance the contrast so the tiny microscopic circuits are actually detectable by the math.
Which perfectly sets up step 3, feature extraction. This is where those mathematical filters we talked about earlier come in. The system starts pulling out the lines, the sharp edges of the circuits, or localized interest points like corners and metallic blobs.
Exactly.
So does this mean the computer's basically playing a high-speed, multidimensional game of connect the dots before it even knows what it's looking at?
That is an absolutely excellent way to visualize it. It's looking for structural primitives. It doesn't know it's a microchip yet. It just knows there are 20 parallel lines and a shiny metallic blob over here.
Just shapes and lines.
Right. And this raises a really important question about the fundamental nature of this pipeline, which is data reduction. Because once you have those features, you move to step 4, detection and segmentation.
Right, the system has to decide which specific regions of the massive image are actually relevant. It segments the image, essentially isolating the specific tiny solder joint on the chip from the completely useless background of the conveyor belt.
It's separating the signal from the noise.
Exactly. And finally, step 5, decision-making. The true genius of this pipeline isn't just its ability to take in massive amounts of data. It's the system's ability to ruthlessly throw data away.
Yes. It distills millions of pixels and all those complex geometric features down to a single, simple, application-specific choice. Is that isolated solder joint cracked? Pass or fail?
It really is an incredible funnel of information. Billions of mathematical calculations just to say yes or no. And once you perfect that specific pipeline, acquiring, extracting, segmenting, and deciding, you can deploy it literally anywhere.
Anywhere at all.
And the scale of this is staggering right now. For 2024, the leading areas of computer vision were industry, with a massive market size of $5.22 billion. Medicine was at $2.6 billion, and the military sector was just shy of $1 billion.
The real-world applications across those sectors really show how adaptable that five-step pipeline is. Take agriculture, for example.
Oh, the farming applications are wild.
They really are. Engineers have actually developed open-source vision transformer models to help farmers monitor crops in real time.
Okay, I want to clarify vision transformers, because they are a huge leap beyond the CNNs we talked about earlier.
A massive leap.
Yeah, older models look at an image chunk by chunk, sliding that little filter around like we said. But a vision transformer looks at the entire image all at once.
It's a holistic view.
Right. It uses an attention mechanism to understand how a brown spot on the bottom of a leaf relates to a yellowing edge on the complete other side of the plant. And because of that holistic view, this model can automatically detect strawberry diseases from visual data with 98.4% accuracy.
It's revolutionary for global food security. And then in medicine, it's doing very similar pattern recognition, but it's looking inside us.
Instead of a strawberry, it's a human.
Exactly. Systems can extract information from ultrasonic or X-ray images to spot tumors, detect arteriosclerosis, or even measure blood flow. It's doing the grueling pixel-by-pixel analysis that human eyes just get too fatigued to do reliably over an 8-hour shift.
And then you have autonomous vehicles and space exploration. We're talking about everything from the obstacle warning systems in consumer cars using cameras and LiDAR, all the way to NASA's Curiosity rover and the Chinese Space Agency's Yutu-2 rover navigating the Moon and Mars.
It's everywhere.
So what does this all mean? When you step back, you really have to marvel at the universal language of light and geometry. The exact same foundational pipeline being used to inspect tiny strawberries in a field in California is steering a robotic rover through the radioactive dust of Mars.
It is incredibly versatile. And in those really high-stakes environments, like the military and autonomous driving, there is a specific concept that becomes absolutely critical: sensor fusion.
Sensor fusion, meaning more than one camera.
Exactly. It is rarely just one camera operating in isolation. A self-driving car might use visible light cameras to read a red stop sign, thermal imaging to spot a pedestrian walking in the dark, and radar to calculate the exact speed of an oncoming truck.
That's a lot of incoming data.
It is. The system automatically fuses all that disparate data to reduce the complexity of a busy intersection. It has to make life or death strategic decisions in real time based on a synthesized view of the entire world.
Okay, so we've seen how this technology spans from agriculture to space, but there is one application from the research that absolutely blew my mind. We are actually using computer, quote-unquote, sight to replicate the human sense of touch.
Yes. Tactile feedback for robotic hands. This is honestly one of the most cutting-edge and frankly brilliant engineering workarounds I've ever seen in the field.
I have to explain this mechanism to you because it is so clever. To give a robotic finger a sense of touch, you would normally assume they just, stick a pressure sensor on the outside of the finger.
Right? That's what we tried to do for years.
But those external sensors break, or they just aren't sensitive enough for delicate work. So instead, engineers suspend a tiny camera inside a flexible, hollow silicon dome. And this dome acts like a squishy fingertip.
Right.
And embedded evenly all throughout the inside of that silicon dome are little painted point markers, just little dots.
And when that robotic finger presses against a physical surface, say an egg or a soft piece of fabric, the silicon naturally deforms and squishes.
Right. And the internal camera is just sitting in the dark inside the finger, just watching those point markers shift around in real time. The computer then analyzes that visual shift, the microscopic movement of the dots, to determine the exact physical imperfections of the surface it's touching.
It's brilliant.
It's literally like looking at the shifting shadows on a blanket to figure out exactly what kind of object is hiding underneath it.
That analogy is spot on. Grasping objects effectively and instantly adjusting grip strength based on the texture and slip of an item has historically been one of the absolute hardest mechanical challenges in robotics.
It's so hard for machines to pick things up gently.
Exactly. Traditional strain gauges on the outside of a robotic hand are just too fragile. So by translating the physical sensation of touch into a visual processing problem inside a protected silicon dome, engineers have completely bypassed those hardware limitations.
They use vision to solve touch?
They're using vision algorithms to solve a mechanical physics problem. It's beautiful.
It's just a stunning evolution. I mean, we started this deep dive looking at a group of researchers in 1966 who naively thought they could solve artificial sight as a quick summer project.
And look where we are now.
Yeah, today we are looking at this invisible, hyper-complex matrix of algorithms that can diagnose life-threatening diseases, drive cars through rush hour traffic, and literally allow robots to feel the textures of the world using cameras hidden inside silicon fingertips.
It is a profound testament to decades of rigorous interdisciplinary science. You have physics, biology, mathematics, and engineering all converging to teach a machine how to interpret our reality.
And it's really something to remember as you go about your day. Every time you glance at your phone and it unlocks using facial recognition, every time you drive a modern car with lane assist, or even every time you eat a piece of automatically sorted, perfectly right produce from the grocery store, you're relying on this technology.
You're relying on that five-step pipeline.
Exactly. You are interacting with machines that are constantly acquiring, extracting, and deciding based on the visual world.
But as these systems become more and more integrated into our daily lives, there's a final detail from the research regarding typical tasks that I really think we should consider before we go.
Oh, right.
It brings up the highly complex and somewhat controversial topic of emotion recognition.
Right. Using facial recognition to not just identify who you are, but how you're feeling.
Exactly. Computer vision systems are currently being trained to classify human emotions based on the microscopic geometric movements of our facial expressions. However, the data explicitly points out that psychologists strongly caution against this.
Psychologists are sounding the alarm.
Yes. Decades of psychological research suggest that internal, subjective emotions cannot be reliably detected from facial expressions alone. A smile doesn't always mean happiness. A furrowed brow doesn't always mean anger.
The human face is incredibly nuanced. I mean, we mask our feelings all the time or express them in ways that completely contradict our internal state.
Precisely. Which leaves us with a lingering, somewhat provocative question to ponder. As computer vision becomes perfectly, ruthlessly precise at mapping the geometry of our physical world down to the exact millimeter of a smile, what happens when we deploy that exact same geometric math to judge our inner feelings?
That's a heavy thought.
Are we genuinely creating a machine that truly understands us, or are we just building a highly efficient automated system for misinterpreting human nature?
Wow. It really brings us right back to the beginning, doesn't it?
Mm-hmm.
We've spent decades trying to teach a machine to translate light into a 3D world. But when it comes to the muddy waters of human emotion, the camera might see everything, but the machine still might be completely in the dark. Thanks for joining us on this deep dive.